All right, this is our review, pages 3 and 4. First one here is asking us to find all the critical numbers for this function. So what we want to do in this is to make sure that we get our derivative right. Whether we can solve it or not may be a different story, but let's make sure we get this derivative right. It is a product rule, so the derivative of x is 1, leave the other function alone, plus x times now the derivative of this, which would be, if you think of this as 4 minus x to the 1/2, you're going to have the half come down, leave the 4 minus x alone to the negative 1/2, and then times the derivative of negative x, which is negative 1. Okay. If we rewrite this and kind of, what we want to do next is we want to set this equal to 0 and try to solve it out, right? So I'm going to have 4 minus x. Over here, I'm going to bring this negative here, make this a minus. The x is going to stay up top, but the 2 will go down and this will go down, and I'll rewrite it as that. You don't have to do that, but I think it makes the next part a little easier to understand. So you would get a point or 2 for the derivative, all right, and then setting it equals 0 helps get you going here. So I'm going to add this over. Square root of 4 minus x equals square root of 4 minus x. And then what I'm going to do is I'm going to go ahead and multiply. So that's going to give me x equals 2 square root of 4 minus x times square root of 4 minus x. And that's 2 times this times itself, which anytime you take a square root times itself makes it go away. So now I get x equals 8 minus 2x. Add that over. Divide by 3, and we get x equal to 8/3. That's our critical point. All right. So that's our answer to part A. We don't know anything about it, whether it means anything or not, but we'll do that for part A. So for part B, it says use the first derivative test to find local max and minimum. So we only have one critical point to try. It's 8/3, right? So if we pick something less than 8/3, let's say we pick 0 when we put it into this derivative, I get square root of 4, which is 2, minus 0, and it doesn't matter what that is. So 2 minus 0 would be a positive. So that means our function is increasing up to 8/3. Then if I put something bigger than 8/3, say I put 3 in, all right? 4 minus 3 is 1, square root of 1 is 1. So I get 1 minus 3 over 2. So 1 minus 3/2 is a negative half. I get a negative there. That means our function is decreasing on that spot. So that means we have a relative maximum at x equal 8/3. Okay. It also means that would be enough to prove that 8/3 is the absolute maximum of this function, or as where the absolute maximum would be located, because the function was increasing up to it and decreasing after it. It never changed on either side of that. So that would be enough for the AP grader to know that that would be your absolute maximum. But we're going to go ahead and show it the old-fashioned way here. C says find the absolute maximum from -5 to 3. So what we do here is we take our x and our g of x in this case, and we say, all right, our endpoints are -5 and 3, and our critical point was 8/3. So if I were to put -5 into this function, I would get -5 times the square root of 9. So -5 times 3 is -15. All right, if I put 8/3 in here, I'm going to get 8/3 minus the square root of 4 minus 8/3. Now that's not something I think they would ask you to do, so I'm just going to go ahead and do that. 8/3 times the square root of 4 minus 8/3 gives me 3.079. Okay. And if we were to put a 3 in there, we would get 3 times the square root of 1, which is 3 times 1 or 3. All right, so here we go. We got our maximum where we thought at 8/3, and we have our minimum back down here at -5. Okay. Now, if you were to take your calculator, put it in, and then make your window go from -5 to 3 and hit graph, you definitely see that. Here's -15, our minimum, and then right up there, you can start to see it's turning at that 8/3, about 2 2/3. All right, and then the graph starts to go down. Now, if you weren't sure about that, you could do what I call a zoom box. And what a zoom box does is it lets you box in a part of your graph that you want to see a little bit clearer. So if I just come over here and I hit enter, and say go down and over, and I just box this in. I said I just want to kind of see what really is going on here. Hit enter. Gives me a little better picture, and then you can kind of start to see where that graph has come up and now is starting to come back down. It's a nice little feature that the calculator has on it. All right. Number 6 here says, here's the graph of f of x. Can you arrange these in order from smallest to largest? Let's get a feel for what they are. So f prime of a is the slope of the tangent line at a, and that is we'll say a big positive, okay? F prime of 0 is the slope of the tangent at 0, and that looks like it's kind of a big negative. F prime of c is the slope of the tangent at c, and that sure does look like it's 0. The average rate of change from c to d is the slope of the tangent line from c to d. So that slope right there is positive, but it's certainly not as big as the positive was here, right? So that's going to be a small positive. And then letter E says f of b minus f of d over b minus d. What that is another way of saying average rate of change from b to d. And so we're talking about the slope of that line right there, and that's negative, but not as negative as it was at 0. So this is going to be a small negative. All right, if I'm going from smallest to largest, the big negative would be the smallest value, so b, then the small negative, e, then 0, c, then the small positive, and then finally the big positive. So that would be our order right there. And then for number 7, it says, what does b have to equal in order for this function to be differentiable? Now, I don't know if we can make this or not. We're going to figure it out. So the first thing we have to do is see if it's continuous. If this function is not continuous, then we can't take the derivative. And the way we figure that out is we're going to put 0 in for here, we're going to put 0 in for here, and we're going to see if we get the same value, all right? So if I were to put 0 into the top, I get the cosine of 2 pi over 3. That's the cosine of 120 degrees, and that would be a negative 1/2. If I put 0 into here, I get a negative 1/2. So sure enough, this is continuous. We have an agreement at the transition point, right? Now, in order to be differentiable, we have to have agreement when we take the derivative of the top and the derivative of the bottom. So let's go ahead and do that. F prime of x will be derivative of the top, negative sign, keep the inside the same, times the derivative of the inside, which is just 1, so that's going to stay there. That's for x greater than or equal to 0. And for the bottom, the derivative will just be b. All right? So now, if I were to put 0 in here, I get the opposite of the sine of 2 pi over 3. So the sine of 2 pi over 3, the sine of 120 degrees is square root of 3 over 2. We're taking the opposite of it. So we get a negative square root of 3 over 2. That's the derivative on the top. In order to be differentiable, the derivative of the bottom has to agree. So that means b has to equal that right there. So again, what we did was we put 0 in to start with to see if they were continuous. Do they meet at a point? You know, like we don't want to jump discontinuity. And then what we did secondly is to see if when they meet, is it a smooth transition? Is it a sharp turn? Or does it just glide nice and smoothly there? That's what we were doing on that second part.